Hi everybody, Jonathan here. In this video, I will be telling you about section 5.1, which is all about the area problem. So, ever since elementary school, we have been learning how to calculate the areas of various shapes. However, now that we know about functions, we can get all sorts of new shapes that we don't have formulas for the area for. So far, we've got formulas for the area of a rectangle, of a triangle, of a circle. But how could we, say, find the area underneath the curve of y equals x squared? This is sort of like a triangle, but it's got this curvy side. So in order to solve this, we are going to use the power of limits. In fact, we are going to develop one of the most powerful ideas in calculus, and that is to solve a problem, find an approximate solution first. Once you have an approximate solution, then if you can turn it into a system of approximate solutions and get a better and better approximation, you can try and take a limit of that system. And if all the cards fall into the right places, then you can actually evaluate that limit. Now, I made an activity in GeoGebra to illustrate how we're going to go about this process. So in this GeoGebra app I made, you can type in any function you like. We've got the function f of x equals 5 minus x squared. What we want to do is find the area enclosed by this function and the vertical line x equals minus 2, the vertical line x equals 2, and the x-axis. So it's not filled in here, but it's all this area under the curve between x equals minus 2 and x equals 2. So at our first attempt of approximation, we are going to try to fit a rectangle over the graph, but we've got to relate it to the graph. And we're not doing this in an intelligent way or anything, we're just doing it to get started. So right now, for the base of the rectangle, it's just going to go all the way from x equals minus 2 to x equals 2. For the height, I'm just using whatever the distance is up to the graph at x equals 2. And that's our first approximation. As you can tell, this is not a very good approximation. We're missing out on all this area up here. To improve it, we can increase the number of rectangles. So I changed n equals 2. Now, what I've done is I've split the interval minus 2, 2 up into two intervals. Over each interval, I'm using the endpoint of the right interval and the distance up to the graph to be the height of a rectangle, and I'm using the width of that rectangle to be the base of the rectangle. And then we can calculate those areas. So in the notation we usually use, the height of each rectangle is going to be f of xi, as I goes from 1 to n as we slowly increase the number of rectangles. The base of each rectangle, it's always the same. We're going to divide the subinterval up into equal pieces. If we divide it into n equal pieces, then it's got to be the length of the interval over n. So the great thing about this is we can now increase the number of rectangles. So first off, when we had n equals 2 rectangles, the one on the left is an overestimate. The rectangle has this area that's not under the curve. And the one on the right is an underestimate. But we have no idea if the over and underestimates cancel each other out. But we're going to increase the number of rectangles. And as we increase the number of rectangles, you can see here what the approximate area is. And we're going to keep on increasing the number of rectangles. But now I've got n equals 15 rectangles. And it's not perfect, but you can see that the area of all the rectangles is a decent approximation of the area under the curve. On the left here, we've got a bit of an overestimate. We've got these little bits outside the area under the curve. And on the right, we're missing some of the area under the curve. And if we're lucky, those will approximately cancel each other out. But the point is, I can keep on making more and more rectangles. If I go up to about n equals 25, the spaces outside of the area get smaller and smaller. And I can go all the way up to n equals 40. And now you can kind of tell that the rectangles aren't perfect, but they're very close to the actual area. And then we can read off what the actual approximation is. Here we think the area is about 14.66. So that is great, and by taking the limit as n goes to infinity of the areas of all these rectangles, we do in fact get the exact area. In the next section, we'll actually try to calculate these limits. This is the kind of formula that's exactly right but not super useful because it's a limit of an expression whose the number of terms you're adding changes as n goes up. So it's a very difficult limit to evaluate directly. We will learn some ways of evaluating it for some simple functions. But then, thinking ahead a little bit, it turns out there's an amazing workaround that we'll learn about when we learn about the fundamental theorem of calculus. In the meantime, feel free to visit this app. You can change the function to be anything you like. So, I don't know, I'll make the function be sine x, why not? This only really works when the function is positive. So we'll make the function, so you got to make sure you choose the endpoints such that the function is positive between them. And then, having done so, you can adjust the number of rectangles and get your approximate areas. That's all for now. Have fun.